Okay, so what you're looking at might seem a little complex, but it's actually a map to the invisible architecture that runs our entire digital world. Databases. Honestly, they're the unsung heroes behind pretty much everything you do online. So, in this explainer, we're going to break down exactly how they bring order to the absolute chaos of modern data.
I mean, just think about your day. That flight you booked for your vacation, the show you just binge watched, even the ads you saw that were maybe a little too specific. Every single one of those things, every click, was powered by a super sophisticated database working like crazy behind the scenes.
Now, picture this. Millions of people are all doing that stuff at the exact same time. So, how on earth does it all stay organized? How does it stay secure and accurate? How do we stop the whole system from just collapsing into a total mess of lost reservations and wrong bank balances?
Well, to really get it, we have to look back at how things used to be. In the old days, data was just stuffed into simple files. Imagine a messy folder on your computer. It was a complete nightmare. You had data redundancy, which just means the same info was copied all over the place. If you updated it in one spot but forgot another, boom, you've got inconsistent, conflicting data. It was hard to get what you needed, and if two people tried to use it at once, oh, that was a recipe for disaster. Database systems were literally invented to fix every single one of these problems.
So what's the secret to avoiding all that chaos? It's having a really good plan from the get-go. And in the database world, that plan is called the Entity Relationship Model, or you'll just hear it called an ER model. Think of it like an architect's blueprint for our data. It maps out exactly what we need to store and how all the different pieces are going to fit together long before anyone writes a single line of code.
And what's wild is that this whole grand blueprint is built on just three super simple ideas. First, you've got an entity. That's just a fancy word for a real-world thing, like a student or a course. Next, each entity has attributes, characteristics, like a name or an ID number. And finally, you have relationships, which is just how these things connect. For example, an instructor advises a student. That's it. That's the whole foundation.
So that abstract blueprint becomes something real in what we call the relational model. This is where our data finally gets organized into these nice, simple tables that we all kind of recognize, right? It looks just like a spreadsheet. Each row is a specific entity, like our instructor, Einstein, and each column holds one of its attributes, like his department or his salary.
Okay, but hold on. If all our data is now split up into all these different tables, how do we connect everything back together? The answer is with keys. A primary key is something that makes each row in a table unique, like a student's ID number. No two students can have the same one. But then the real magic happens with a foreign key. This is a field in one table that points back to the primary key in another table, and that's what creates the powerful link.
Let's look at exactly how this works, because this is where it all clicks. See that role now? It's the primary key in the student table. It makes every student unique. Now look over at the course table. That very same role no is used there as a foreign key. This is the digital glue that connects a course to a student. It makes sure we always know who's taking what. It's what keeps the data's integrity intact.
Okay, so our database is designed, the tables are all linked up. Now what? How do we actually, ask it questions to get information out? Well, we use a query language, something like SQL, and the deep down logic behind it all is something called relational algebra. It sounds intimidating, but it's just a formal way of playing with tables. Relational algebra gives us some really powerful tools. First up is select. Think of this like a super strict filter for your rows. If we set a condition, like, hey, show me all the rows where column D is greater than 5, the select operation instantly grabs only the rows that match. It just throws everything else out. And the next big operation is project. So if select is a filter for rows, project lets you pick and choose your columns. It basically creates a whole new, smaller table that has only the specific attributes you care about. It's perfect for creating simpler, more focused views of your data.
But, even with a great blueprint, design problems can sneak in. Just look at this table. See how the details for the comp sci department, the building, the budget are repeated over and over again for every instructor? That's called redundancy, and it's not just messy, it is dangerous. Why? Well, what if the budget changes? You have to remember to update it in every single one of those spots. If you miss just one, your data's now wrong. It's corrupted.
Thankfully, there is a formal process for fixing these kinds of design flaws. It's called normalization. The best way to think about it is like a tune-up for your database. It's a step-by-step way to find that repeating data and then break up or decompose that big, messy table into smaller, much cleaner tables. This gets rid of all sorts of weird problems that can pop up when you're trying to add, delete, or change information.
And here it is. This is the result of normalization. That one big table has been split into two beautiful, clean ones, an instructor table and a department table. Now, the budget for computer science is stored in exactly one place. The tables are linked neatly by the department name, and what we have is a design that's efficient, reliable, and totally free of that dangerous redundancy.
All right, so our database is now beautifully designed. It's clean, efficient. We should be done, right? Well, not quite. There's one last massive challenge to deal with. What happens in the real world when thousands or millions of people are all trying to book tickets or transfer money at the exact same time? How does the system handle that?
The answer is a concept called a transaction. A transaction is just a way to group a bunch of operations into a single unit of work. The classic example is a bank transfer, right? You have to take money out of account A and you have to put money into account B. Both have to happen. It's an all-or-nothing deal. If any part of it fails, say the power goes out midway, the whole thing gets undone, so money doesn't just vanish.
And to make these transactions totally bulletproof, they're protected by 4 guarantees. We call them the ACID properties. Atomicity is that all-or-nothing rule we just talked about. Consistency makes sure the database is in a good, valid state before and after the transaction. Isolation is huge. It means that if 2 transactions are happening at once, they can't see each other's messy, halfway done work. And durability guarantees that once a transaction is finished, those changes are permanent. They'll survive even if the whole system crashes.
So from designing the blueprint with ER models, to building the house with a relational model, cleaning it up with normalization, and then making it earthquake-proof with ACD transactions, these are the core ideas that bring order to data chaos. As the source material puts it so well, they truly touch all aspects of our lives.
These principles are working for you, right now, behind every app and every website you use. They would keep your data safe and consistent. But that leaves us with one last, kind of scary question. We rely on these guarantees to be perfect, every single time. So what really happens when one of them fails?